In this video, we're going to introduce optimization, specifically working with word problems. We've already seen how to find maxima and minima values by looking at critical points and then analyzing those critical points using the first and second derivative tests. However, we haven't had to define the function we want to maximize or minimize, and that's usually the most challenging part in optimization problems. Let's start by taking a look at an example. In this classic optimization challenge, we have a farmer who wants to build a rectangular enclosure to contain some livestock. They have a certain amount of fencing available, and one side of the enclosure will be part of an already existing building, like a barn. So there's no need to put a fence on that side. The question is, what should the dimensions be for each side to maximize the area of the enclosure? The first thing in any optimization problem is to figure out what your actual goal is. What are you looking for as the end product? And here, we want to know specifically what's the quantity that should be maximized in this example. Take a moment to think about it, and then we'll check in. All right, notice that there is a number of different elements in the sentences here in the paragraph describing the problem, but the key phrase is this last sentence. What should the dimensions of each side be to maximize the area? And that tells us right away that the area is what we want to maximize. So what that also tells us is we are going to need a formula for the area based on some other values in the problem. That's where we're going to look next. So what are the variables in this question and how are they related? That's a natural next step once we've decided what we're aiming for. You may want to draw a picture. That is a severe understatement. You do want to draw a picture. In fact, in any of these geometric optimization problems, without a picture, you're likely going to make some kind of serious mistake. So let's start with that picture idea. And notice you can draw something like this, but it looks kind of like a square. We don't want to assume too much at the outset. Sometimes it's helpful to deliberately draw not optimal solutions so that we can see what the elements we can play with are. So what we have here is the wall that can be part of our enclosure, and then all this incorporated around this side is fencing. And what can we choose? Well, we can choose how much fencing to use both in this length and its matching length on this side and the other side here. So what we could do is define variables. Let's call this, because it's drawn as a vertical stretch here, let's call that h for height, and this part here as width for the left to right distance in this diagram. Now those two are not directly related to each other except to say we know that the total fence length is going to equal 120 meters. And that's going to be made up of 1h plus 1 width plus another h on the far side, or 2h plus w. And that's one relationship between the variables. The other variable relationship that's going to be relevant is the actual area. Let's call that A. And because this is a simple rectangle, we'll have the area is equal to height times width. So just based on the geometry of the problem and some of the text, we have a relationship between the variables, the area related to height and width, and the height and width tied to the fencing lengths. So now express the quantity to be optimized in terms of the variables above. We actually already have that. However, it's important to recognize that we can't just pick whatever we like for both of these variables. If we have a big H, then we're going to have a small w, or we can have a small height and then a big width. Those are going to be our options. So I shouldn't leave both of these variables in there as is. Fortunately, we can do a quick substitution here and recognize that if we know the height, say, let's bring it to the other side, 120 minus 2h. If we know what the height is, then we can calculate through this and get just w left over. So if w is equal to 120 minus 2 times the height, then our area can be written as height times, instead of this W, we replace it with that. And this has just one variable, specifically one independent variable. If you know what h is, you choose the height of your fencing, you will be able to calculate the area. Now, because we're going to be working with h, it makes sense to ask what kind of values could h take on. So the domain for h, excuse me, this is not always related to the formulas. In fact, this h formula here is totally valid for any value of h, negative, positive, huge, small, doesn't matter. In optimization problems, the domain tends to be something we derive from the shape that we're looking at. In particular, we'd better have h greater than or equal to 0. It doesn't make any sense to have negative lengths of fencing. You could have a quibble about 0, but in principle, sure, we can have a 0 length fence. It'll just give us 0 area, so we know it's not the best, but it is possible. The other thing we might note is that if we have 120 meters of fencing, then the most we can have is 60 on one side, and then going back the other way, another 60. So h had better be less than or equal to 60, otherwise we run out of fencing and we can't physically build the configuration we would be talking about. Again, would we want equal 60? Probably not, but we'll let the... Again, would we want h equal to 60? Probably not, but having a closed domain makes a lot of our optimization calculations easier, and it's certainly a feasible solution, even if it's not the best. And domain is about feasibility, not about optimums yet. We'll get to the optimums shortly. So we want to use the techniques learned earlier in the course to maximize the function on this domain. So we have our area, which is equal to h times 120 minus 2h. And this is on the domain. H is between 0 and 60. So note that this is a closed domain, and A is continuous on it. I can plug in any value of h here. There's not going to be any weird discontinuities. These things are going to help us when we go to prove that whatever optimum we find is actually the global optimum out of all the possible choices. Next step. If we have a function and we want to find its maxima and minima, we're going to look for critical points. But if we're looking for critical points, that means we need the derivative of a, and we can do that with this product, but it's a bit of a hassle. So let's first rewrite a to be equal to 120 h's minus 2h squareds, because it's more derivative friendly. If we're going to calculate derivatives, we might as well have a formula that makes that a bit easier. And product rule is a hassle. So we've got a, and then we can find the derivative of that, and it's going to be with respect to h is our variable here, or if you like, using prime notation, you can use a prime. If h is our variable, our derivative is going to be 120 minus 4h. And that gives us the rate of change of the area as we dial in up or down the length of the sides of the fence that we're building now. Because we're looking for critical points, we are then going to set that equal to 0. Because critical points are the points where we have that value equal to 0. Well, that turns out to be a breeze to solve because we have a simple linear function. We're going to get h is equal to 30. So one single critical point. Well, that's handy because now it leads us to a way to find the global maximum. We don't even need the first and second derivative tests for this because we are working on a closed interval. If we talk about h being between 0 and 60, if we sketched A, I don't know what it looks like, but I do know at 30 something interesting happens. And what we can do is figure out the area when h equals 0, the area when h equals 30, and the area when h equals 60, and the highest one of those is going to be the optimal area length. So we're going to find the area when h is 0. We can plug it into this formula up here, and we simply get, 0. So when there's no fence length vertically, we get 0 area. We could have predicted that. We can predict what A of 30 is using either this formula or this one. We'll use the top one for simplicity. 30 times 120 minus 2 times 30 is 60. 60 times 30 is 1,800 meters squared. And last but not least, if A is 60, there we'll have 60 times 120 minus 260 is another 120. That's also equal to 0 meters squared. So what we can do is actually sketch out the graph of A here. We know that there's a critical point. Let's add our axes here. There's a critical point here with slope 0. We have a value of 0 here, a value of 0 here, and no other critical points. So pretty much the only shape we can have here is that arc that you see in front of you. And because A is continuous on a closed and bounded domain, and we check the 3 values that were possible, the 2 endpoints and the single critical point, which is all the critical points, A of 30 is the max area. And what does that come with? Well, we really want to know the dimensions of the fence we're going to build. Our h is going to equal 30 meters, and we can work backwards and find the width if we just go back one step. The width of the fence we're going to use is 120 minus 2 times that, so 120 minus 60, or 60 meters. Those are the optimal dimensions of the fenced-in area. And that's the solution to our first application of optimization to a word problem.